So, welcome back student to the next class of nonlinear optics and its application. So, today we will going to study one very important thing called optical phase conjugation. For the last few classes we have been studying the 4-way mixing and the corresponding applications. So, optical phase conjugation is some sort of 4-way mixing which has some application that we will going to discuss in this class. So, what is 4-way mix, what is phase conjugation under 4-way mixing? So, before going to that topic, let us try to understand what is basically the phase conjugation. So, the term optical phase conjugation as written here in this slide is usually used to describe the wavefront reversion property of a backward propagating optical wave with respect to the forward propagating wave. So, a wave is propagating in the forward direction, and if the same wave is propagating in the backward direction, then this is nothing but the conjugate wave of that, and this phase conjugate is related to that property. So, there are three different examples are shown in this particular slides. If you see, in one case we have a mirror and the wavefront which is parallel to the mirror is propagating towards the mirror and reflected back. If there is no distortion in the mirror, the same wavefront will be reflected from this mirror, and this is an example of an ideal plane wave, and this ideal plane wave which is reflected back from the mirror is nothing but the phase conjugated wave. In the similar way, that means from this example you can readily understand that the light that is propagating in one direction will be reflected by the mirror and propagating in the exactly in the same direction. So, there is a directional property. So, it is not that light is reflecting and then after reflection it is moving in other directions also. That normally happen when we see something, then that is the case, that light is reflecting in all the direction, that is why I can see that particular object. But here the thing is that the light is reflecting from the mirror and then propagating exactly in the same path and moving in the opposite direction. Another example of the ideal phase conjugation system is the ideal spherical wave. So, here instead of having a mirror which is a straight mirror, we have a spherical mirror, and this spherical mirror have some sort of curvature, and if I launch an wavefront with the same curvature, it will go and then reflected back from this particular mirror, and we eventually have a reflection. But the important thing is the light is propagating in this direction, and after reflection it is again coming to this particular direction. So, direction is not going to change. So, light is moving in the same path. These two examples are related to mirrors. The mirrors I am talking about is a normal mirror, and now the third example is something which we will going to discuss in detail, and this is called phase conjugate reflector. This is a special mechanism on that, and we will describe this mechanism in today's class. But the important thing here is that any shape of wavefront, you can see that this is a distorted waveform, and if this distorted waveform is reflected from this phase conjugated reflector, what happened? We will return back the same wavefront, even though it is a reflected, even though this is reflected, but the distortion is there. So, that means during the reflection there is a possibility that it will not going to move in the same direction, but here we find that it will going to move in the same direction as this is a phase conjugate reflector. So, how by using the 4-way mixing we can generate this kind of reflector, we will going to study today, and also we will find that this kind of reflector not only reflect the light under some sort of phase conjugation light, it will going to reflect also amplification properties are there. So, reflected light can be amplified also. So, this can be only happen if the system behave in a nonlinear fashion. So, nonlinear optics is directly related to this kind of phenomena. So, let us discuss what really happen and what is the physics behind that. Okay. So, this is again the same picture, and maybe this picture will be more useful for the students, because here you can see that for the regular mirror, if the light is coming from one part and then reflected back, so this reflection may not be in the same direction. So, you can see that this is a light where the wavefront is not the wavefront is not really a plane wave, but it is some sort of distorted like this after moving some distance. And what happened that because of this distortion, so the light will be reflected from this mirror, and this reflected light can be moved in whatever the direction it likes. But for the same light, if it falls on a phase conjugated mirror, then what happened that the light will go here, and then from here it will again reflected back in the same direction. So, this is a very unique kind of mirror, and if some image is distorted, then by using this phase conjugated mirror, we can make this image more perfect. So, distortion can be removed by this phase conjugated mirror, because whatever the shape is coming to this mirror, and after the reflection we will have a similar kind of phase. So, further distortion is not possible here. So, since the light is propagating the same path, so that is an added advantage, and because of that we can find a distortion free system by suitably use these things. So, now let us try to understand in detail exactly what is going on. So, this is, as I mentioned to the start of this class, that is it nothing but the 4-way mixing problem that we have been discussing for last few classes. So, here we have a 4-way mixing, but all the waves are having the same frequency. That is the first thing that we need to note, that here this is not a non-degenerate kind of 4-way mixing, this is a heavily degenerate 4-way mixing, because all the wavelength are same. For all wave, the wavelength is same or the frequencies is same, and we call this frequency simply omega. But the one important thing here, there are 4 waves associated with this system. So, chi3 is a nonlinear system, we can see that there are 4 waves associated for this phenomena, and these 4 waves are shown here with 4 different colors. In all cases the frequencies are same, only thing is that the directions for 4 cases are different. In first case E3 and E4, the frequency is omega. So, if I write these 2 plane wave, it will be simply omega t both the cases. But since the direction is different, in one case the wave is moving in the forward direction, and other case the wave is reflected back. So, in one case if I write the plane wave in the form e to the power I kz minus omega t, in the next case I should write e to the power minus kz minus omega t. So, this is the same wave, but it is moving in opposite direction. Here also E1 and E3 we use as a pump. Why we will going to use as a pump we will describe, but you should note that during this course we study many amplification process, and this is in some sort of amplification process I am talking about. So, that is why the pump term is there. So, whenever we have some amplification or amplification some wave, so the associated pump should be there. So, pump basically gives the energy to the wave or the signal, and signal get amplified. Here also we will going to get the similar kind of phenomena. So, these things are basically behave as a pump. But the important thing is that this is not in the direction of z, but this is some arbitrary direction and moving in the opposite direction. So, in one case if I write it is k dot r minus omega t, since this is the arbitrary direction I cannot write it is kz minus omega t, because it is not in the z direction at all, you can see that. So, it is k dot r minus omega t, in other cases it is minus k dot r minus omega t. As I mentioned, the frequency is same for all the cases, only the directions are different. So, here in the right hand side all the 4 waves are written E1, E2, E3 and E4. E3 and E4 are moving in the z direction. So, that is why this is their plane wave structure. E1 and E2 which behave as a pump is moving some arbitrary direction, say r. So, that is why the plane wave structure is k dot r minus omega t, and here also minus k dot r minus omega t, because it is in opposite direction. So, 4 waves are now in our hand. So, next thing that we will do, we will use the simple process that we have been using in studying the 4 wave mixing. So, nonlinear polarization, we need to find out what is the nonlinear polarization for that. So, nonlinear polarization is nothing but epsilon 0 chi 3, the total field cube, because this is the third order process. So, in third order process we know that the total field has to be cubed. So, that means the nonlinear polarization inside this system is E1, E2, E3, E4 and cube of that, where E1, E2, E3, E4 is written in the right hand side. Now, we need to find out the polarization that will give rise to the wave E4 and E3. Why E4 and E3? Because let us go back to the previous slide, then maybe we can understand these things better. So, E1 and E2 behave like a pump. So, we are not going to study the evolution of E1 and E2, because normally pump is very high amplitude with very high amplitude, and we are not bothered about the evolution of the pump normally. Here we will do the same thing, E1 and E2 will be pump. So, it will give rise to some sort of energy it will supply some sort of energy to the wave E3 and E4. So, evolution of the E3 and E4 is important. Since the evolution of the E3 and E4 is important, this E3 and E4 is important, we need to find out what is the source term of E3 and E4. Mind it, E4 is not here. So, because of the mixing of these 3 waves E3, E2 and E1, E4 will going to generate. This is a 4-way mixing. So, mixing of 3 frequencies can generate a other frequency, and that is the thing we need to find out, the how E4 will going to evolve inside this system. So, in order to find out how E4 will going to evolve, one thing that we need to derive first is the nonlinear polarization corresponds to the E4, and also E3 if I want to find out what is the evolution of E3, because E3 is also important, this is some sort of signal. So, P nonlinear of 3 we need to find out. So, these two nonlinear polarization term basically the source term of E3 and E4. So, that is why our first aim is to find out the nonlinear polarization for E3 and E4, and here we find that E1, E2, E3, E4 is there. So, if I say I want to find out the nonlinear polarization of wave 4, so eventually what I am trying to find out, that a phase of the form e to the power of minus kz minus omega t. This is for 4, because we know that the E4 wave is moving in the opposite direction. So, the phase of these things is in this form. So, obviously, the P nonlinear term should have this kind of phase, and that will be the source term of E4. So, the next question is how to form E4 by using E1, E2, E3, where E1, E2, E3 is given here, and how I will get this stuff, this phase, which is very easy, because this kind of calculation we have been doing for last few classes. So, here if I see, so E1, E2, E3, E4 cube are there. So, I need to find out how E4 will going to generate using E1, E2, E3. E1 has a phase this, E2 has a phase this, and E3 has a phase this with complex conjugate. So, very easy to find out what should be the form of E4 and if I know the form of E4 is e to the power of I minus k z minus omega t, that means if I multiply these two stuff E1 and E2, I will this minus kr, this kr will cancel out, we will have a phase with a term 2 omega t, and if I make a complex conjugate of these things, then I will have minus kz and then plus omega t. If I add all these two, all this term, then I will eventually have minus kz minus omega t, which is exactly this term. So, that means I need to multiply E1, E2 and then I need to multiply the E3 star with that. So, exactly the same thing is done here, because it is a plus b plus c plus d whole cube. So, a cube plus b cube plus c cube plus d cube, this term will be there. Also the mixing term is also there. So, in this mixing term, if three terms are not same, we know the degeneracy factor 6 should be multiplied with that. So, that is why this 6 term is here. All the fields have half term with them. So, that is why if I multiply 3 fields, so 1 by 8 will be here and the phase will be sitting simply like this with a complex conjugate term. So, this is a very simple way to find out the p nonlinear 4. I believe you can easily find out if you are given a different kind of phase, you can readily find what should be the value. In the similar way, exactly in the similar way, you can find the nonlinear polarization term corresponding to the field E3. In case of E3, everything should be same, and just by inspecting the nature of the field, you can readily find out that just replace E3 to E4 star and you will readily get this term. This is an important term, this is a phase term, and we are looking for this phase term, that this phase term has to be equal to the phase term of E3, then only I can say that this is a nonlinear polarization term corresponding to E3. So, once we find the corresponding phase term and when I combine E1, E2, E3 to get E4 or E1, E2, E4 to get E3, then we are ready, because p nonlinear term is in our hand. Mind it, our aim here is to find out the evolution of E3 and E4, and in order to find the evolution of E3 and E4, we need to find out the nonlinear Maxwell's equation, and this nonlinear Maxwell's equation p nonlinear is a source term. So, very first thing is to find out the source term. We are doing that throughout this course. So, I believe now you are familiar with this procedure. So, this is a very old kind of equation. This equation, I do not know how many times I am using, but again this is our nonlinear Maxwell's equation, and this nonlinear Maxwell's equation for E4 field. So, for E4 field we have a source term, and this source term should contain p nonlinear 4. So, when p nonlinear 4 term is there, it is easy because p nonlinear 4 I already derived in the previous slide. So, this is our structure. This is the same structure, that we have an incident wave and two other waves moving opposite direction, and this is our z, this is the z direction, and these two behave as a pump, and the mixing of E1, E3, E2 and E3, the mixing of E1, E2 and E3 give rise to another term E4, and that term should have a phase exactly the phase exactly in the way which is exactly in the opposite direction. So, if the phase of E3 is kz minus omega t, which is propagating in the forward direction, if I say this is a forward direction, then we will going to find out what should be the form of the wave that will be moving out, and it will be exactly in the opposite direction of E3. So, the mixing of E3, E2 and E1 give rise to a wave E4, and E4 will moving in the opposite direction of E3. That is the simple thing that we are doing right now. So, in order to find out the evolution of the E4, we need to study the nonlinear Maxwell's equation or nonlinear wave equation, whatever. So, this is a source term, and E4 we know that E4 already it is written here what should be the form. So, now if I try to find out this grad square value of the E4, this is the same old equation that we are using, the second order derivative of the E4 here is the amplitude. Curl E, mind it, curl E is the total field here, curl E4 is the total electric field of total electric field that is moving in the opposite direction. E is the amplitude and the phase term is written here. So, E4 will be derived twice with respect to Z, E4 will be derived once and then the kz is there. So, kz will be there. So, 2I kz and then k square E4. This is the derivation or the grad square value of E4 once the E4 value is in our hand. Obviously, the phase term will be there in this way. And next I will calculate the time derivative of this term. E4 is half, curl E4 is equal to half E4 e to the power I minus kz minus omega t. So, when I make a time derivative, so omega square term will come out with a negative sign. So, here we can see omega square is coming out with a negative sign here, half will be as usual and we will have the phase. And finally, the source term. So, P nonlinear we have already derived in the previous slide. So, let us go back to the previous slide and check what was the value. It was 1 by 8 epsilon 0 chi 3 6 E1 E2 E3 star minus kz minus omega t. So, if I make a derivative of this term with respect to t and if I make that derivative twice, then what happened, this omega will come outside and there will be a negative sign, that is all. So, we will do the same thing here in this slide, and if we do, we will find it should be 3 by 4 and this quantity, the 6 it was, if you remember, it was 6 and there was 8 term. So, this 6 and 8 will boil down to 3 by 4, mu 0 epsilon 0 is already there, mu 0 is here, epsilon 0 is already there, chi 3, omega square will come out, and this is the amplitude term, this is the important term. This amplitude term we know it will come, it will be a term E1, E1, E2, E3 star, and this is a corresponding phase. So, when I put all this equation together, we know that these two term will cancel out, and this term will cancel out because this term will cancel out because the slowly varying approximation. This term and this term will cancel out because if I replace this k in terms of mu and epsilon, then it will be exactly the same this term. So, this term and this term will again cancel out, and finally, we will have 2 I k with a negative sign, dE4 dz is equal to 3 by 4 with a negative sign mu 0 epsilon 0 this. So, this is our equation for E4. So, we can further modify this equation or further simplify this equation, and if we simplify this equation, it will be simply like this. It will be simply like this, dE4 dz is equal to minus of I 3 by 4 chi 3 omega square k c square E1 E2 E3 star. So, k again I can make it a more compact form, the usual form, that chi 3 omega divided by n c, 3 by 4 is the term with a negative I and E1 E2 E3, where if I put this quantity, if E1 and E2 are constant, if I consider this is a constant, as I mentioned, E1 and E2 is the amplitude of this pump. So, if the amplitude of the pump, if the pump is strong and if I consider that there is no depletion of the pump, then the amplitude of the pump E1 and E2 become constant. So, entire term will remain constant, and if I write this constant as a coupling term, then finally, we will have a very important equation in our hand, which is the evolution equation of E4, and which is dE4 dz is equal to minus of I kappa E3 star. Exactly in the same way, if I derive E3, it will be simply this. So, E3 E4, the differential equation of E3 E4 we derive. Now, what we will do? We have two coupled equation and we will do our usual procedure, that to solve this. So, if I make a derivative of E4, so in the right hand side this term will be we have a derivative of this term. So, E3 is Ez and E3 Ez star is this. So, I just replace here. So, I will get this equation. So, this is a very straightforward differential equation, homogeneous differential equation whose solution is sinusoidal. So, I write the solution here. So, the solution of E4 is in our hand. Once we have the solution of E4, then we can readily find what is the solution of E3, because E4 and E3 are related to this differential equation. So, this differential equation suggests that E3 will have this particular form. I am moving little bit fast here, because I believe this basic calculation you can do by yourself and can understand easily, that this is a solution of this kind of differential equation and this is a solution of this where the equation is given. Well, once we have these two solutions in our hand, the next thing is to find out the boundary condition. So, boundary condition is important here. As I mentioned, E3 is coming from this side. This is our E3, but E4 is generated inside and then moving out. So, initially E4 when come and reflect here. So, that means at z equal to L, eventually we should not have any kind of E4, so as it is reflected. So, if I put this boundary condition and also if I write that E3 at z equal to 0 is some value E3 0, because here we have some E3, then we will have E4 L is 0, because E4 L is 0. If I put z equal to L, then we have a relationship, and this relationship suggests that A equal to minus of B tan of mod of kappa L, and E3 0 is also this quantity. Well, once we have the value of A and B, the relation of A and B, so this relationship of A and B in our hand, which we derived in the last slide. So, E4 I can write in total. I just replace A and B and write the total equation of E4. Also, we know what is E4 0. That means, if this is the system, I have what is here at z equal to 0 point and z equal to L point we know. So, now at z equal to z point I know, because z equal to L this quantity is 0. So, that means something is reflected like this here. So, now if I try to find out what is the reflection coefficient, because E3 is here and it is reflected, E4 is reflected back. So, the reflection coefficient is simply E4 at 0 point z equal to 0 point divided by E3, this is incident wave at 0 point and mod of square. So, from this equation which we have already derived, it is easy to find that it is something like tan square kappa L. Now, we know that tan square value can have a range. So, this reflectivity suggests it is tan square kappa L. So, if kappa L is greater than 4 pi by 4, then the reflectivity is greater than 1. That means, we have some sort of amplification, as I mentioned. If it is 1, then whatever we have in the input, we will have the same thing as output. Now, if it is greater than 1, then that means we have amplification. So, that is an added thing, and this amplification is possible because of the fact that we are pumping. If you remember this system, we have some sort of pumping, and this pumping basically give rise to the fact that some sort of amplification may possible. Now, if it is pi by 4, then R tends to infinity. So, we have some sort of wave without any kind of input, is something like that. So, it is nothing but the oscillation. So, several possibilities or several things can be happen here, and this is a very interesting process, but the important thing is that you can have a reflected wave with just opposite phase. So, this is really a phase conjugated kind of wave. So, using this 4 wave mixing, we can have the conjugate wave, or this conjugate wave is very useful in different or in order to remove the distortion and this kind of things. So, physics today we have understood, and there are several conditions. In one condition it is reflected, in one condition it is oscillated, and in one condition it is even amplified. So, amplification is also possible. This is added advantage because of this nonlinearity. So, with this note, let me conclude here. In the next class we will going to start a completely new topic, which is Raman scattering. So, see you in the next class, and thank you for your attention.